Tonight, we're going to explore one of the oldest and quietest puzzles in all of science. It hides in plain sight, in something you have seen 10,000 times and probably never questioned: the darkness of the night sky. Step outside on a clear night, far from the glow of any city, and look up. And it is worth pausing on those words, far from any city, because most of us almost never see a truly dark sky anymore. From a town or a suburb, the glow of streetlights and houses scatters up into the air and washes the faint stars away, leaving only the brightest few dozen to shine through. You have to travel out, into the countryside, into the desert or the mountains or far out to sea, to a place where the artificial light falls away, before the real sky reveals itself. And even then, it does not happen all at once. Your eyes need time to adjust, perhaps 20 or 30 quiet minutes in the dark, as they slowly grow more sensitive, the pupils widening, the eye reaching for every faint scrap of light. Wait for that, and the sky deepens and fills in front of you, more and more stars emerging from the black the longer you look. And when your eyes have fully opened to the night, you will see stars. If your eyes are rested and the air is still and the moon is down, you might count a few thousand of them. That is, in fact, about as many as a person can take in at once. Under a truly dark sky, the unaided human eye can make out somewhere in the range of 2,000 to 3,000 stars at any one time. And across the whole of the sky, over the course of a year, only around 9,000 are bright enough to see without a telescope at all. It feels like a great glittering multitude when you first look up, and in a way it is. But notice the number: a few thousand points of light, scattered across the entire dome of the heavens. And here is something quietly remarkable about those few thousand stars, something worth holding on to. Every single one of them, every star you can see with your unaided eye, belongs to our own galaxy, the Milky Way. And not just to our galaxy, but to our own small neighborhood within it. Almost all of the stars visible to the naked eye lie within a few hundred or a few thousand light years of us, which sounds enormous, and is, but is only the tiniest local pocket of a galaxy that stretches 100,000 light years across. The stars you see at night are your near neighbors, the closest and brightest suns in our immediate corner of one galaxy, and that soft, faint band of misty light that arches across the darkest skies, the one the old stories called the Milky Way, that is the galaxy itself, seen edge on from the inside, the combined glow of hundreds of billions of stars too far and too faint to separate, blurred together into a river of light. We live inside it, and we are looking out through it, so already there is a hint of the strangeness to come. What you see on even the darkest, clearest night is not the universe. It is a tiny local sample of one galaxy among an almost unimaginable number of others. And now notice what lies between those scattered stars. Between every pair of them, around every bright point, stretches an enormous, settled black. We tend to think of the stars as the main event, the thing worth looking at, the reason we tilt our heads back in the first place. But look again, gently, and take in what actually fills most of the view. It is not the stars, it is the dark. The black is the dominant feature of the night sky, vast and continuous, and the stars are only the scattered exceptions sprinkled across it, a thin dusting of light on an overwhelming field of shadow. Here is what makes that strange, the thing that has quietly troubled careful minds for centuries. The universe is not a small place holding a sparse handful of stars. It is vast almost beyond the reach of words, and it is crowded with stars in every direction we have ever looked. Our own galaxy, the Milky Way, that faint river of light, holds somewhere between 100 and 400 billion stars all on its own, and our galaxy is one among an almost unthinkable number of others. When astronomers have counted the galaxies scattered through the reach of their telescopes, the estimates run into the hundreds of billions, and by some careful reckonings as high as 2 trillion galaxies, each one a vast island holding its own immense crowd of suns. Everywhere we point our instruments, in every patch of sky we have ever studied closely, we find more of them. The cosmos is not sparse. It is brimming. It is full to overflowing with light. So consider what that fullness should mean. If stars fill the universe in every direction, on and on without any gap we can find, then pick any direction at all, any single point on the dark dome above you, and follow your line of sight outward from it, out past the nearest stars, out through the breadth of our own galaxy, out across the gulfs between galaxies, further and further into the depth of space. By simple geometry, that line should eventually arrive at the glowing surface of some star, maybe a near one, maybe one unimaginably distant, but a star all the same. The next line of sight beside it should land on another star, and the next on another still. With a universe truly full of stars going on without end, there should be no direction you could possibly look that does not, sooner or later, terminate on something bright. Every line of sight should end on a stellar surface. If that was so, the night sky would not be dark at all. It would be a solid, seamless wall of light, not scattered points on a black background, but an unbroken sheet of stellar fire, every gap between the near stars filled in by more distant stars shining through behind them, and those gaps filled by stars further still, layer upon layer, until the whole dome above you blazed as bright and as uniform as the surface of the sun. There would be no night. There would be no soft shadows the way we know them. The sky at midnight would glare down as fiercely as the sky at noon, in every direction at once, with no dark anywhere to rest your eyes upon. So why is it dark? That is the contradiction, and it is a real one. It is not a trick of language or a riddle with a clever answer hidden in the wording. The geometry is sound. The universe really is full of stars, more of them than any mind can hold, scattered in every direction. And yet the sky overhead is mostly black, cool and quiet and deep, with only that thin scattering of points to break it. Something in that simple chain of reasoning must be quietly, profoundly wrong, and finding out what it is will take us on a long and unhurried journey. It will lead us first to the air just above our heads, to ask whether the darkness is something our own atmosphere is doing to us, then out past the airless worlds of our own solar system, to skies that look nothing like ours, into the great telescopes that stare into a single dark patch of sky for days at a time, and what they find waiting there. Back across 4 centuries to the careful thinkers who first felt the weight of this same question. And finally to an answer so unexpected, so gentle and so strange, that it quietly changes what the word darkness even means. The dark, it will turn out, is not what we think it is at all. But none of that is for right now. None of it is anything you need to hold or solve or carry with you tonight. So let yourself settle. Find the position that feels easiest, the one where nothing is asking anything of your body, and let the weight of the whole day begin to leave your shoulders. There is nothing here that requires effort. You do not need to follow every thread, or keep the order of things straight, or remember a single fact by morning. The ideas will arrive slowly, one gentle step at a time, with plenty of room to breathe between them. And if you drift off somewhere in the middle, somewhere out among the stars or the centuries, that is not a failure. That is exactly as it should be. The point is not to arrive anywhere. The point is to drift. Let your breathing slow on its own, without forcing it. Just notice it for a moment, the quiet rise and the soft fall, and let each exhale loosen something a little more. Feel the surface beneath you holding your weight, so that you do not have to. The room around you is safe and still. The dark around you is calm. And far above the roof, far beyond the air and the clouds, and the thin blue edge of the atmosphere, the same vast and starlit puzzle waits, patient as it has been for billions of years, in no hurry at all. It will keep. It has kept for a very long time. If you find comfort in these slow journeys through the cosmos, you are always welcome to follow along for more, but there is nothing you need to do now except rest. Let the light stay low. Let the thoughts and the small worries of the day grow distant and quiet and small, the way a city's lights shrink to nothing as you rise away from it. We have a long, easy night ahead of us, and we are going to spend it wandering gently out toward the edge of everything, and back again, softly, together. There is time for all of it. There is no rush at all. So take one more slow, easy breath, and let it go, and let's begin. Before we go anywhere far, let us stay close to home for a while. The first answer most of us would reach for is sitting right above us, and it is worth taking apart slowly. When you picture the dark night sky, it is easy to assume the darkness has something to do with our own world. The sky is dark at night and bright in the day, and that rhythm is so familiar, so woven into every day we have ever lived, that we rarely stop to ask what is actually doing the lighting and the darkening. It feels like the sky itself simply switches on and off, the way a lamp does, as if night were a kind of absence that arrives on its own. But the sky does not make its own light. It only passes along, or scatters, or hides the light that comes from elsewhere. So before we blame the cosmos for the dark, we should make sure the dark is not simply something our own air is doing to us. Let us look first at the daytime, because the daytime hides a clue that is easy to miss. Here is the small strangeness in the ordinary day. When the sun is up, the whole sky is bright. Not just the part of it where the sun sits, but all of it, from horizon to horizon, a great, glowing dome of blue. Step into the shade of a building at noon, where the sun cannot touch you, and look up at a patch of sky far from the sun, and it still shines. The light is reaching you from a direction where there is no sun at all. So where is that light coming from? The sun is a single point, a fierce little disk in one corner of the sky, and yet somehow its light arrives at your eye from every direction overhead. Something is taking the light that streams out from that one point and spreading it across the entire sky. That something is the air itself. Our atmosphere is not perfectly empty and invisible the way we tend to imagine it. It is a vast ocean of molecules, mostly nitrogen and oxygen, countless trillions of them in every breath-sized parcel of it. And when sunlight pours into that ocean, the molecules intercept the light and fling it back out in new directions. A ray of sunlight that was heading somewhere far from your eye strikes a molecule of air, scatters off it, and a small piece of that light gets redirected. It may scatter again off another molecule, and another, bouncing its way through the air, until at last some of it comes down to you from a direction the sun never occupied. Multiply that by the uncountable molecules in the long column of air above your head, and the result is a sky that glows everywhere the sunlight reaches into it. The blue you see at noon is not the sun seen directly. It is sunlight that has been caught and turned and handed off, molecule to molecule, until it finally arrives at your eye from a patch of sky the sun is nowhere near. This process has a name, and it is one worth knowing gently. because it explains not only the brightness of the day, but its very colour. It is called Rayleigh scattering, named for the British physicist Lord Rayleigh, John William Strutt, who worked out its mathematics in the 1870s. The idea sounds technical, but the heart of it is simple and rather beautiful once you sit with it. When light meets particles much smaller than its own wavelength, as sunlight does when it meets the tiny molecules of our air, the shorter wavelengths get scattered far more strongly than the longer ones. Let us take that slowly, because it is the key to the whole colour of our sky. Think of sunlight not as a single white thing, but as a blend of every colour woven together, from the long, lazy waves of red at one end of the rainbow to the short, quick waves of blue and violet at the other. These are not just different colours to the eye. They are different physical lengths of wave. Red light ripples along with a wavelength roughly twice as long as that of blue light. And Rayleigh scattering does not treat these lengths equally at all. It strongly, dramatically favours the short waves. The effect grows in proportion to the inverse fourth power of the wavelength, a precise way of saying that even a small difference in wavelength makes an enormous difference in how strongly the light gets scattered. Because blue light has a wavelength a little more than half that of red, that fourth power relationship means blue is scattered something on the order of 5 to 10 times more readily than red. The short waves are flung about the sky. The long waves mostly carry straight on through. So picture what happens as sunlight crosses the air above you. The blue component is constantly being knocked sideways, scattered out of the direct beam, and sprayed across the whole dome of the sky, while the red and orange mostly travel straight through toward wherever they were already headed. The air becomes a kind of delicate blue prism, quietly pulling the blue out of every sunbeam and painting it across the heavens in every direction. That is why the day sky is blue. You are not seeing the sky's own colour. You are seeing the particular colour of light that our air most loves to scatter. And you might wonder, if shorter waves scatter even more strongly than blue, why the sky is not violet, since violet is shorter still. Part of the answer is that the sun sends out a little less violet to begin with, and part of it is that our eyes are simply more sensitive to blue than to violet, so the sky settles into the blue we know, a blend the air scatters and the eye is built to notice. And here is a quiet confirmation of all this, hiding in something you have seen 1,000 times without thinking about it. The clouds. Clouds are white or grey, not blue. If the same air that scatters blue were doing the scattering in a cloud, the clouds would glow blue too. But they do not, and the reason is lovely in its simplicity. A cloud is not made of air molecules. It is made of water droplets, and those droplets are far larger than a molecule, large enough that they are no longer small compared to the wavelength of light. And when the scattering particles are large like that, the delicate blue favouring rule no longer applies. Large droplets scatter all the colours of sunlight more or less equally, red and green and blue together. And when you scatter all the colours equally and mix them back up, what you get is white. This different kind of scattering, of particles comparable in size to the light itself or larger, has its own name. Physicists call it Mie scattering, after the physicist Gustav Mie, who described it in the early 20th century. So the white of a cloud and the blue of the clear sky are two faces of the same underlying physics, sorted simply by the size of the thing the light bounces off. Tiny molecules give you blue, large droplets give you white. The sky tells you, in its colours, what it is made of. And the very same blue scattering effect, running the other way, gives us the warm colours of sunset. When the sun sinks low toward the horizon, its light no longer comes down to you through the short, straight column of air overhead. Instead, it has to slice in at a shallow angle, through a far longer slant of atmosphere, sometimes many times the thickness of the noon air. Along that long, slanting path, so much of the blue has already been scattered away to other parts of the sky that very little of it survives to reach you directly. What does survive, what makes it all the way through that long reach of air, are the long red and orange waves that the air mostly lets pass. And so the sun itself, and the sky around it, glow red and gold. The sunset is not the sky adding red. It is the sky having scattered the blue away over a long journey, leaving the warm colors behind. The same molecules that make the noon sky blue make the evening sky burn orange. The only thing that changed is how much air the light had to travel through to find your eye. And the darkness does not arrive the instant the sun goes down, which is itself a small piece of the same story. After the sun has slipped below the horizon, the sky stays lit for a while, softly, gradually fading. This is twilight, and it happens because even when the sun is hidden from where you stand, its light is still pouring into the upper air, high above you, where the atmosphere is still in sunlight even though the ground is not. That high, still-lit air goes on scattering light down to you for a time, a glow that slowly deepens and cools as the sun sinks further below the horizon, and less of the air above remains lit. Twilight can linger for an hour or more, the blue draining slowly out of the sky, and only when the sun has dropped far enough that no air above you catches its light at all, does the true dark finally settle in. Even the falling of night is a story about scattered sunlight, fading gently as the last lit air goes dark. Now hold all of that in mind, the brightness and the blue and the burning sunset, and the slow fade of twilight, and notice the single thing they all share. Every bit of it depends on sunlight being present to scatter. The glow of the day is sunlight, redirected by the air. The blue is scattered sunlight. The red of evening is what is left of sunlight after a long passage. The glow of twilight is sunlight still catching the high air after the ground has fallen dark. None of it is light the sky makes on its own. And that tells us exactly what should happen when the sun is finally, fully gone. At night, deep night, the sun has rolled well below the horizon, and its light no longer pours into any of the air above you, not even the highest reaches. There is still air up there, of course, every bit as much as there was at noon, those same countless molecules waiting. But now there is no flood of sunlight for them to catch and scatter. With nothing to redirect, the air falls quiet and becomes, for our purposes, very nearly transparent. It turns into a clear, dark window. And through that window, you are no longer looking at scattered local sunlight. You are looking straight out, past the air entirely, at the universe as it actually is. The dark you see at night is not the air switching off, the way a lamp does. It is the air finally getting out of the way, drawing back the bright blue curtain it hangs up by day, and letting you see the true face of the cosmos behind it. This is the quiet clue I mentioned. If the darkness of night truly came from our atmosphere, then a world with a different atmosphere ought to have a differently colored darkness, and a world with no atmosphere at all ought to behave in some revealing way of its own. We do not have to guess. We have been to other worlds, with cameras and with people, and with patient robotic landers, and we can simply look at their skies and see. Start with the moon, the nearest of them. The moon has essentially no atmosphere at all, only the barest, thinnest whisper of stray atoms that hardly deserves the name. With no ocean of molecules to scatter the sunlight, there is nothing to spread the sun's light across the lunar sky. And so, on the moon, the sky is black, not only at night, but in the full blaze of lunar day. An astronaut standing on the moon at high noon, with the sun glaring fiercely overhead, and the grey ground around them lit brilliant and stark, looks up into a sky as black as the deepest night. The sun is a savage white disk, but the sky surrounding it is pure darkness. This is the strongest image to carry from all of this, so let it form slowly. Picture an astronaut beside a single boulder on the moon. One boot rests in sunlight so direct and unfiltered that it dazzles, every grain of dust on it sharp and bright. And the other boot, just inches away, sits in the boulder's shadow, plunged into a dark so complete it looks carved out of the vacuum itself. No soft glow fills that shadow, because there is no air to carry any light into it. On a world without an atmosphere, light and dark sit side by side with a hard, clean edge between them, like a line drawn with a blade, and the daytime sky stays utterly black. The moon shows us, as plainly as anything could, that a sky's brightness is the gift of its air. Take the air away, and even a sun-drenched world wears a black sky. Now travel a little further out to Mars. Mars does have an atmosphere, but a thin one, less than 100th as dense as our own, and made mostly of carbon dioxide rather than nitrogen and oxygen. It also carries, almost always, a fine haze of reddish dust, lifted from its surface and held aloft in the air. Because the Martian air is thin and dusty rather than thick and clear, it scatters light quite differently than Earth's air does. The suspended dust does most of the work, and dust grains are larger than air molecules, so they do not follow the clean blue favoring rule of Rayleigh scattering. By day, the Martian sky is not blue, but a pale, dusty tan, a soft butterscotch color, because the dust scatters the warmer tones and tints the whole sky with something close to the color of the ground. And then comes the detail that delights nearly everyone who first hears it. On Mars, the sunsets glow blue. Around the setting sun, in the patch of sky closest to it, the light takes on a cool bluish tone, the reverse of what we see on Earth. The fine dust scatters the light in such a way that the blue lingers near the sun, while the rest of the sky stays warm and tan. This is not a guess or an artist's fancy. The rovers that have spent years crossing the Martian surface have photographed these blue-tinged sunsets again and again, sending the images home across the gulf between worlds. They are real, a quiet wonder waiting on another planet. And Mars tells us the same lesson the moon does, only painted in color rather than in black. The sky you stand under depends entirely on the air that surrounds you. And then there is Venus, which makes the point most dramatically of all. Venus is wrapped in an atmosphere so thick and heavy that it would crush you, a dense blanket of carbon dioxide far weightier than our own air, topped with high clouds of sulfuric acid. That cloud cover is so bright and so reflective that Venus throws a large fraction of the sunlight that reaches it straight back into space, which is part of why the planet shines so brilliantly as the evening and morning star in our own sky. But for anyone able to stand on the surface beneath that shroud, the sun as a disk simply does not exist. The light has been scattered and diffused so thoroughly on its long way down through the dense air and the deep clouds that it arrives at the ground from every direction at once, with no source you could ever point to. There is no bright spot marking where the sun is. There is only a thick, even golden orange murk, a permanent diffuse glow filling the whole of the sky, dim and heavy and sourceless, like standing inside a vast lit fog. The The sun is up there somewhere above the clouds, but the atmosphere has smeared its light across the entire sky until the sun is nowhere in particular and everywhere at once. Venus shows us the far extreme of what an atmosphere can do, taking a single brilliant sun and dissolving it into a uniform, sourceless haze. We could go on, world by world, and the lesson would only repeat itself. Stand on Mercury, the closest planet to the sun, and you would find a sky much like the moon's. Mercury has only the faintest trace of an atmosphere, so thin it is barely there, far too sparse to scatter light into any kind of glow. So on Mercury, despite the sun looming more than twice as large and many times as fierce as it appears from Earth, the sky around it stays black even at the height of day, the sun a blinding lamp hung in a field of darkness. The same rule holds everywhere we look. Where there is thick air, there is a bright and coloured sky. Where the air is thin, the sky darkens. Where there is no air at all, the sky is black even under a blazing sun. 4 worlds, 4 skies, and not one of them looks like ours. The black noon of the airless moon, the dusty butterscotch and the blue sunsets of Mars, the sourceless golden haze of Venus, the dark midday of sun-scorched Mercury. The lesson sits right there in the comparison, impossible to miss. The colour and the brightness of a sky are local things, properties of whatever air a particular world happens to wear, not properties of the universe at large. Our blue day and our red sunset belong to Earth alone. Step onto another world and the sky changes completely, even though the very same stars and the very same sun lie behind it all. Which brings us back gently to our own night. If the brightness of a sky is something the local air provides, then the darkness of our night sky cannot be blamed on the air. Quite the opposite. The air is what gives us the bright blue day. When that air goes quiet at night, with no sunlight left to scatter, it does not create the dark. It simply stops hiding what was always there behind it. The night sky is dark not because of anything our atmosphere is doing, but because of what lies beyond it. We have cleared the air, in every sense of the phrase. The darkness is not a trick of our planet. It is the genuine, unfiltered face of the cosmos itself, looking back at us through a window that the falling night has finally wiped clean. So the atmosphere is not the culprit. We have ruled it out by looking at our own day, at the physics of scattering, and at the skies of 4 other worlds. The dark we see is the universe's own, and that makes the original puzzle sharper rather than softer, because now we know we are looking straight at the real thing. If the cosmos truly is full of stars in every direction, and the air is no longer in the way, then the question we started with returns to us undimmed. Why, with that window wiped so clean, is there still so much black to see? To answer that, we have to learn to trust what our eyes and our cameras are actually telling us about the dark. And as we will find next, even our most ordinary photographs of space carry a small mystery of their own, one that has confused a great many people over the years, and one that points us, quietly, straight toward the heart of the matter. So let us trust the window, now that we have cleaned it, and let us start by looking at the photographs, because here is a small puzzle that has tripped up a great many people, and untangling it will teach us something important about how we see the dark. Think of the famous images of space, the ones you have surely seen. An astronaut standing on the grey lunar surface, white spacesuit gleaming in the sun. The space station drifting above the great curve of the Earth, its panels catching the light. A close pass by one of the planets, its bands and rings sharp against the void. Look at the background in those pictures, behind the astronaut, behind the station, behind the planet. It is black, empty. There are no stars in it at all. Just a smooth, featureless dark, as if the photograph had been taken against a sheet of black paper, rather than against the star-filled cosmos we have just spent so long describing. This has bothered people for decades. If space is full of stars, and these cameras are out in space with no atmosphere in the way at all, the cleanest view imaginable, then where are the stars in the pictures? Some have taken the question further and treated the missing stars as evidence of something sinister. The famous claim about the Apollo moon landings leans heavily on exactly this point. The argument goes that if the astronauts had truly stood on the moon, the photographs would show a sky thick with stars, and since the skies in those photos are black and empty, the whole thing must have been staged in a studio somewhere on Earth. It is a claim that sounds reasonable for about as long as it takes to think it through. The moment you understand how a camera actually works, it falls apart quietly. The empty black sky is not evidence against the moon landings. It is precisely the sky those photographs were guaranteed to produce, and a studio fake, if anything, would have been more likely to get it wrong by sprinkling in stars that should not be there. To see why, we need to talk gently about light and exposure, because a camera does not see the way your eye sees. Your eye is a marvelous adaptive instrument that adjusts itself constantly and blends what it takes in over time, so that you can hold a bright lamp and the dim corners of a room in the same single glance. A camera is far more literal than that. A camera opens a shutter, lets light fall onto its sensor for a fixed span of time, and faithfully records whatever arrives in that window, no more and no less. How much light it gathers depends on two things working together. One is how wide the opening, the aperture, is held. The other is how long the shutter stays open, the exposure time. Open the aperture wide and hold the shutter long, and the camera drinks in a great deal of light. Stop the aperture down narrow and snap the shutter brief, and it sips only a little. It helps to picture what is actually happening inside the sensor while that shutter is open, because it makes the whole mystery dissolve. A modern digital camera, including the cameras on spacecraft and the great telescopes, gathers light using a sensor made of millions of tiny light-sensitive cells, called pixels, etched into a chip of silicon. The technology comes in two main kinds: the charge-coupled device, or CCD, and the more recent CMOS sensor, but the basic idea is the same in both. When a particle of light, a photon, strikes one of those tiny cells, it knocks loose a small electric charge, which the cell quietly holds onto. The longer the shutter stays open, the more photons fall on each cell, and the more charge it collects, like a row of little buckets left out in the rain, each one slowly filling. When the exposure ends, the camera reads how much charge has gathered in every bucket, and from that vast grid of measurements it builds the image. A bright part of the scene fills its buckets quickly. A faint part fills them slowly, drop by drop. Now, the brightness of the things being photographed in space varies far more than your eye, which evens everything out, ever lets you feel. An astronaut in a white suit standing in unfiltered sunlight on the moon is staggeringly bright. The sunlit panels of the space station, the cloud tops of the Earth, the day-lit face of a planet, all of these are blazing, lit by the same fierce sun that lights our own midday, and with no air to soften it. To photograph something that bright without it washing out into a featureless white smear, where every bucket has overflowed and all detail is lost, the camera must do the opposite of drinking in light. It must hold the shutter open for only the tiniest fraction of a second, and stop the aperture down narrow, taking in as little light as it can, so that the bright subject fills its buckets to just the right level and lands as a clear, properly exposed image. And that very setting, the one that captures the bright astronaut perfectly, is far too brief to capture a star. Stars, for all their grandeur, are faint pinpricks by the time their light has crossed the vast distances to reach us. To record a star on a sensor, you need to let the light accumulate, to leave the shutter open for seconds, sometimes for many minutes, patiently gathering those scarce photons until enough have piled up in the bucket to register as something real. 1,000th of a second exposure aimed at a sunlit astronaut gathers nowhere near enough starlight to leave a mark. A handful of photons from a faint star might fall on a cell in that brief instant, but a handful is not enough to be sure it was starlight at all, and not just the faint random flicker that exists in any electronic sensor, the gentle background fizz that engineers call noise. Below a certain level, a real but feeble signal cannot be told apart from that fizz. That threshold is the noise floor, and the faint starlight in a short exposure falls beneath it. The starlight is there, it is arriving, but it is too faint, and the exposure too brief, for the camera to separate it from the dark, so it records as black. This is the heart of it, and it is worth saying plainly. You cannot photograph a brilliantly lit foreground and a field of faint stars in the same single shot, not with one exposure, because the two demand opposite settings. To catch the stars, you would have to expose so long that the astronaut would burn out into a shapeless blaze of white, every bucket overflowing. To catch the astronaut, you must expose so briefly that the stars vanish into black. The camera must choose, and in every one of those famous images, it chose the bright subject in front of it. The black, empty sky is not the absence of stars in the universe. It is the natural and unavoidable result of a correct exposure for a sunlit scene. Far from proving the moon landings false, the missing stars are exactly what genuine photographs taken in bright sunlight must look like. So the emptiness in those photographs is a fact about cameras, not a fact about space. The stars are out there in their countless multitudes. The pictures were not built to catch them. And that realization opens a quiet question, one that turns this whole detour around. We've been talking about exposures too short to catch the faint light of the cosmos. What happens if we do the very opposite? What if, instead of 1,000th of a second aimed at something bright, we take one of the great telescopes, point it at a patch of sky that looks utterly empty, utterly black, and leave the shutter open, not for a fraction of a second, not for seconds, but for hours, for days, letting the buckets fill drop by patient drop with every faint photon that drifts in from the dark? What is hiding in that black, waiting for a long enough exposure to draw it out? This is not a thought experiment. It is one of the most extraordinary things humanity has ever actually done, and the story of it is quietly thrilling. In the mid-1990s, the astronomers operating the Hubble Space Telescope made a daring decision. Hubble's observing time is precious beyond words, fought over by researchers all around the world, every hour of it accounted for and assigned. And the director of the Space Telescope Science Institute at the time, an astronomer named Robert Williams, proposed spending a large block of that priceless time doing something that struck many of his colleagues as close to reckless. He wanted to aim the telescope at a patch of sky that contained, as far as anyone could tell, nothing at all. Not a bright galaxy, not a famous nebula, not a known object of any kind. Just a small, dark, empty-looking speck of sky up near the handle of the Big Dipper, chosen precisely because it seemed to hold nothing that would get in the way, and because it sat in a direction where our own galaxy's light and dust would not block the deeper view. and he wanted to stare at that nothing for 10 straight days. It was a real gamble. If the patch truly was empty, 10 days of the world's finest telescope would be 10 days lost, and the criticism would be considerable. But the reasoning behind the gamble was sound, and it traced straight back to everything we have just said about exposure. A patch of sky looks empty only because the light coming from it is too faint to register in any ordinary brief observation. Leave the shutter open long enough. Gather those scarce photons day after day after day, and perhaps the emptiness would slowly fill in. Perhaps the dark was not empty at all, only patient, only waiting for someone willing to look long enough. Picture the scene in your mind, slowly. The telescope hangs silently in orbit, high above the atmosphere, in the cold and the quiet, turning with the Earth far below it. It locks onto that tiny dark speck of sky, an area so small that, held at arm's length, it would be hidden behind a single grain of sand, and it holds absolutely still, the whole great instrument fixed and steady on that one point. And then it simply waits and watches and collects. Single photons drift in from unimaginable distances and settle onto the detector, one by one, far too sparse at first to make any image at all, just scattered specks. A day passes, another. The faint light accumulates, grain by grain, the way snow gathers on a windowsill through a long and windless night, so slowly you could never catch it moving, yet there it is by morning. For 10 days the telescope drinks in light from a piece of sky that the eye and every short exposure ever taken had quietly written off as nothing. And when the light was finally gathered up and the image assembled, what emerged was breathtaking. That tiny, supposedly empty grain of sky was not empty. It was crowded, it was teeming. The image, which came to be called the Hubble Deep Field, revealed roughly 3,000 galaxies packed into that one minuscule speck. Not stars, galaxies, each one a vast island of hundreds of billions of stars, and there were thousands of them crammed into a patch of sky you could blot out with a grain of sand held at arm's length. Spiral galaxies seen face on, their arms wound tight and bright, others seen edge on, thin as needles of light. Faint red smudges so distant that their light had been travelling for most of the age of the universe to arrive at the telescope at last. A whole deep layered cosmos, reaching back and back and back, hiding inside a scrap of dark that everyone had agreed was nothing at all. Sit with that for a moment, because it is one of the most quietly staggering results in the entire history of looking up. There was nothing special about that particular patch of sky. It was chosen precisely because it seemed empty and ordinary, a piece of dark like any other. Which means that nearly any direction we might have pointed, any random scrap of the black between the stars, would have revealed very much the same thing. The dark, given enough time to speak, fills up with galaxies in every direction we care to look. The emptiness was never emptiness. It was only faintness, and patience dissolved it. And there is something hidden in the colours of those galaxies, worth pausing on quietly, because it is a clue we will need later. Look closely at a deep field image, and you notice that the galaxies are not all the same colour. The nearer ones show their natural tones, the soft white and gold and blue of their stars. But the faintest, most distant ones, the ones whose light has travelled the longest to reach us, tend to glow red, deepening toward a dim, ember-like red the further away they lie. That reddening is not because those galaxies are made of redder stars. It is because their light has been stretched on its long journey across the expanding universe, its waves drawn out longer and longer, sliding from blue toward red as it travels, the most distant light reddened the most of all. We will come to exactly why a little later in our story. For now, simply hold the picture in mind, that in a deep field image, color is a kind of map of distance and of time. The reddest, faintest smudges are the oldest and the furthest, their light setting out toward us when the universe was very young. You are looking at a single image in which the near and the ancient sit side by side, sorted gently by their color, and Hubble did not stop there. A few years later, the astronomers went deeper still. They chose another small, dark patch of sky, this one down in the southern constellation of Fornax, and they pointed the telescope at it for far longer than 10 days. Over the course of months in 2003 and 2004, in many separate exposures gathered together, the telescope stared at that single spot for a total of roughly 11 days of pure light-gathering time, longer and more sensitive than the first deep field had ever been. The result, released in 2004, was called the Hubble Ultra Deep Field, and it reached further into the dark and further back into time than anyone had managed before. Where the first deep field found around 3,000 galaxies, this one revealed close to 10,000, packed once more into a patch of sky no larger than a small fraction of the full moon. And among them were some of the faintest, reddest, most distant galaxies ever seen, their light so stretched by its long journey that it had begun to slip toward the edge of what Hubble could detect at all. These were galaxies as they had been when the universe was very young, only a fraction of its present age, their light setting out toward us when the cosmos was still in its early childhood. The lesson of the first deep field held and deepened. The further we could see, the more galaxies appeared, with no sign at all of the crowd thinning out. And then, in our own time, a new instrument took up the same patient work and carried it dramatically further still. The James Webb Space Telescope, launched at the very end of December 2021 and beginning its first observations in 2022, was built to gather a kind of light that Hubble largely could not, the deep infrared, those long, stretched-out wavelengths into which the most distant and ancient light has been shifted by its journey across an expanding universe. We will come to why that light is stretched a little later in our story. For now, what matters is that Webb's great gold mirror, far larger than Hubble's, and its sensitivity to that infrared light, let it see the earliest, most distant galaxies more clearly than any instrument before it. When Webb produced its very first deep field image, released in the summer of 2022, and aimed at a region of sky around a cluster of galaxies called SMACS 0723, it showed that same kind of dark patch in even finer and farther-reaching detail. Thousands of galaxies again, woven across the black, and among them some of the oldest and most distant ever recorded, their light having travelled for well over 13 billion years to land, at last, on the telescope's waiting mirror. And that first Webb image carried a piece of cosmic ingenuity inside it, a way of seeing further that the universe itself provides for free, if you know how to use it. Look at that image, and you notice something strange near the center. Some of the galaxies appear smeared into curved arcs, stretched and bent, as if seen through the bottom of a wine glass, several of them even repeated, the same galaxy appearing more than once in a great curving sweep. That is not a flaw in the telescope, it is gravity bending light. The cluster of galaxies in the foreground, that SMACS 0723, holds an enormous amount of mass, and according to Einstein's understanding of gravity, mass bends the very fabric of space around it, and light passing through that bent space follows the curve. So a massive cluster acts as a kind of lens, a gravitational lens, gathering and magnifying the light of even more distant galaxies that lie directly behind it, brightening them and stretching them into arcs. The foreground cluster becomes a natural telescope, lent to us by the geometry of space itself, letting Webb peer at galaxies far fainter and further than it could ever reach on its own. It is a beautiful thing that the mass of one set of galaxies should magnify the light of others behind them, that gravity itself should help us see toward the beginning. Webb has used this trick again and again, and with it has pushed even further, picking out faint candidate galaxies that appear to date from only a few 100 million years after the beginning of the universe, astonishingly early, astonishingly far away. The same story, told by an ever-sharper instrument, helped along by the lensing of space itself. Point at the dark, wait, and the dark turns out to be full. So our long detour has brought us somewhere unexpected. We began by explaining why the famous photographs of space look empty, and we found that the emptiness was an artifact of short exposures, a fact about cameras and noise floors, not a truth about the cosmos. Then we turned the cameras around, gave them all the time they could possibly need, and discovered that the dark between the stars is not dark at all, in the way we had assumed. It is layered with galaxies, thousands upon thousands of them in every tiny patch, each one brimming with stars stacked into the distance as far as our finest instruments can reach, and then further than that. The universe really is full of light in every direction, exactly as the original puzzle assumed it must be. The deep fields confirm it with images we can hold in our hands and look at with our own eyes. And that gently is the strange part. Remember where we began this whole journey. The contradiction was this. If the universe is full of stars in every direction, then every line of sight should eventually end on a star, and the sky should blaze with light. We might have hoped quietly that the dark sky simply meant the universe was not as full as it looked, that the gaps between the stars were truly and honestly empty, that there was nothing out there in most directions to catch our gaze. But the deep fields have closed that escape route, gently and completely. They have shown us, photon by patient photon, that the gaps are not empty. They are packed with galaxies all the way down, in every direction we have had the patience to examine. Every line of sight we look along, given enough time, does seem to land on something luminous after all. So the contradiction has not been solved by our journey so far. It has been sharpened. We have cleared away the atmosphere and proven it innocent. We have proven, with the deep fields, that the universe really is dense with light in every direction. And yet the sky our eyes see at night remains stubbornly, deeply, peacefully dark. The puzzle is now standing in front of us in its full strength, with all the easy answers stripped quietly away. And a puzzle this clean, this stubborn, this old, deserves a proper name and a proper history, given to it by the people who first stared into the dark and felt the very same weight we are feeling now. We will meet them next. So we come to the people who felt this before us, because we are not the first to stand beneath a dark sky and sense that something in it does not quite add up. The puzzle we have been slowly building is old, far older than the telescopes and the deep fields, far older than the cameras and the noise floors. It has been quietly troubling careful minds for more than 400 years, and the names attached to it are some of the finest in the long history of looking up. The seed of it goes back at least to the 16th century. In England, in 1576, a mathematician and astronomer named Thomas Digges published one of the earliest descriptions in print of a universe that was not enclosed by a sphere of fixed stars, as the old picture had it, but open, unbounded, scattered with stars reaching outward without limit. Digges was among the first to imagine the stars not as lamps fixed to a single shell around us, but as suns strewn through an endless depth of space. He did not state the paradox of the dark sky in full, but he laid down the very idea, an infinite field of stars that would later make the darkness so puzzling. The thought was planted. It would take other minds to feel its sharp edge. The first to circle that edge seriously was Johannes Kepler, the German astronomer of the early 17th century, the man who worked out that the planets travel around the sun in ellipses rather than perfect circles. Kepler was thinking, in the years around 1610, about whether the universe could truly be infinite, stretching on without end and filled everywhere with stars. And he noticed something that troubled him deeply. If the universe really did go on forever, packed endlessly with stars in every direction, then he felt the night sky ought to be ablaze, every part of it shining. Since it plainly was not, Kepler took the dark sky as a kind of evidence, a clue about the shape of everything. To him, the darkness suggested that the universe must be finite after all, a bounded thing with an edge, a great dark wall enclosing the stars. He read the dark as a sign of a limit. He had the observation exactly right. The dark sky as evidence about the structure of the cosmos, even if the particular conclusion he drew from it would not, in the end, survive. The question surfaced again with Edmond Halley, the English astronomer of the late 17th and early 18th centuries, the man whose name rides on the famous comet that returns to our skies roughly every 76 years. Halley, a friend and supporter of Isaac Newton, turned the problem over in the early 1720s and presented his thoughts on it to the Royal Society in London. He grasped the geometry of the thing, the way an endless field of stars ought to flood the sky with light. He reached for an answer, suggesting that the more distant stars were simply too faint, individually, to add up to much. As we will see when we do the arithmetic carefully, that particular escape does not actually hold, because what the faint, distant stars lose in brightness, they make up for exactly in number. But Halley felt the force of the puzzle, and he wrestled with it honestly. What matters is that the question kept returning. Generation after generation, thoughtful people looked up at the same dark and felt the same quiet wrongness humming beneath it. But the version of the puzzle that truly stuck, the statement that gave the paradox its lasting name, came from another German astronomer, working in the early 19th century. His name was Heinrich Wilhelm Olbers, and he was a physician by training, a man who practiced medicine by day in the busy port city of Bremen and gave his nights faithfully to the sky. Olbers was no mere hobbyist. He was a skilled and dedicated observer, well respected among the astronomers of his age. He discovered comets, and he discovered asteroids, including 2 of the largest in the entire asteroid belt, and a method he devised for calculating the orbits of comets was used for many years after him. This was a serious and careful mind, and in 1823 he published a paper laying out the problem of the dark night sky, with a clarity that made it lasting. He stated it plainly. If the universe is infinite and filled fairly uniformly with stars, the whole sky should shine as brightly as the sun, and the simple fact that it does not demands an explanation. The puzzle had been noticed before him, by Digges and Kepler and Halley and others along the way, and in fairness, it was not Olbers alone who invented it, but his statement of it was the one that endured, and his name is the one history fastened to it. Ever since, we have called it Olbers Paradox. It is a lovely thing, really, that this question carries a person's name. It reminds us that the dark sky is not only a fact of physics, but a human inheritance, a puzzle passed quietly from hand to hand down the centuries, each thinker turning it over, adding a little, none of them quite able to set it down. When you look up tonight and notice the dark, you are joining a long, unhurried conversation that has been going on for more than 400 years, from Digges in his study to Kepler with his ellipses, to Halley among the fellows of the Royal Society, to Olbers at his telescope in Bremen. There is something companionable in that. You are in good company in your wondering, in a quiet line of people who have all looked up at the same dark and felt the same gentle astonishment. Now, Olbers and the others all sensed that the dark sky was telling us something important, but to truly understand what, we have to do the thing they could not quite finish doing. We have to lay bare the hidden assumptions buried inside the simple argument, because the expectation of a blazing sky is not a loose guess or a vague feeling. It is a logical conclusion, and like every logical conclusion, it rests on premises, on things quietly taken for granted. If the conclusion turns out to be false, and the dark sky tells us every night that it is, then one of those premises must be false as well. So we need to find them and name them, these quiet assumptions we have been making all along without ever quite saying them out loud. There are 3 of them, 3 pillars holding up the whole prediction of a bright sky. Let us bring each one out into the light and look at it. The first pillar is that the universe is infinite in size, that it stretches on without end in every direction, holding an endless number of stars. This is the assumption that guarantees that every line of sight, followed far enough, will eventually meet the surface of a star. If the universe were infinite and evenly filled with stars, there would be no direction at all you could look without your gaze, sooner or later, terminating on something glowing. There would always be another star further out to catch your line of sight, and another beyond that. An infinite, star-filled universe leaves no room for any permanent gap, no direction that stays dark forever. The second pillar is that the universe is static, that it sits still, neither expanding nor contracting, with the stars holding their places in a settled, unchanging arrangement. This one matters because it means the light from the stars arrives at us unaltered, undimmed by any motion of the cosmos itself. A star at a great distance shines just as it would if it were near, its light simply spread thinner by the distance it has crossed, but not changed in its essential nature, not weakened beyond what plain geometry would do. In a static universe, distance dims starlight only by spreading it out, and nothing stretches it or saps its energy beyond that. The light you finally receive is the honest, unaltered light the star sent out. The third pillar is that the universe is eternal, that it has existed forever, for an infinite span of time, with no beginning anywhere behind it. This one is more subtle than the other 2, and it will turn out to matter most of all. The reason it is needed is this. Light travels fast, but it does not travel instantly. It takes time to cross space, so light reaching us from a very distant star left that star a very long time ago and has been traveling toward us ever since. For the light from every star, at every distance, to have had enough time to reach us, no matter how unimaginably far away that star may be, the universe must have been around for an unlimited stretch of time. An eternal universe is what ensures that no star's light is still in transit, still on its way, not yet arrived. Given forever, all the light from everywhere has had time to finish its journey and reach your eye. Now hold those 3 together for a moment. Infinite in size, static and unchanging, eternal in time. If all 3 are true, then the conclusion follows with the full force of pure logic. Every line of sight ends on a star. No starlight is dimmed by any motion of the cosmos. and all the starlight from every distance has had time to arrive. And so the whole sky must blaze uniformly in every direction. There is no escaping it if the three pillars all stand firm. And yet the sky is dark. We see it with our own eyes every single night of our lives. The conclusion is false. Which means, with that very same logical force, that at least one of those three pillars must be false. The universe is not infinite, or it is not static, or it is not eternal, or perhaps more than one of those at once. The dark sky is not just a curiosity to wonder at. It is data. It is the universe quietly handing us a clue about its own deepest nature, telling us plainly that at least one of the things we always assumed about it cannot be so. The darkness overhead is, in a real and measurable sense, a kind of reading taken off the cosmos. We only have to learn how to interpret it. That is the quiet power hiding inside Olbers' Paradox, and it is why it has held thoughtful minds for 4 full centuries. A simple act of looking up, of merely noticing the dark, becomes a doorway into the structure of everything that is. The dark is not empty of meaning, it is brimming with it. But before we can read that clue properly, we have to be certain we are reading it correctly. We have to make sure the prediction of a bright sky is as ironclad as it sounds, that there is no loose arithmetic hiding inside it, no quiet place where the distant stars simply fail to add up the way the paradox claims. After all, Halley reached for precisely that escape, the hope that faraway stars might be too faint to matter. So we need to do the geometry carefully, slowly, the way you would set smooth stones one at a time across a stream. We need to see exactly how the light from an endless field of stars is supposed to gather itself into a blazing sky. And we need to find out whether the distant stars really do contribute as much as the paradox insists they do. Picture yourself at the center of everything, which for this purpose you truly are, since every line of sight begins at your own eye. Around you, in every direction, stretches the universe full of stars. Now imagine drawing a vast, thin, hollow sphere around yourself, like a great soap bubble, at some chosen distance. Say it is a sphere whose surface lies 100 light-years out in every direction. This is our first shell. It is a thin spherical layer of space, and scattered through it are some number of stars, all of them sitting at roughly that same distance of 100 light-years from you. Now imagine a second shell, just outside the first, twice as far away at 200 light-years, and a third, further still, at 300. Picture the whole universe as a nested set of these shells, one inside the next, like the layers of an onion, each one a hollow sphere of space centered on you, reaching outward without end. This is simply a way of organizing all the stars by their distance, so that we can add up their light in an orderly way, shell by shell. The question we want to answer is easy to ask. As we move outward from one shell to the next, does each shell send us more light, less light, or the same amount? Because if every shell sends us roughly the same amount, and there are endless shells, then the total light pouring in from all of them together would have to be without limit. That is the crux of the whole paradox, and the geometry settles it cleanly, with a kind of quiet inevitability. Two things change as we move from a nearer shell to a more distant one, and they pull in opposite directions. Let us take them one at a time slowly. The first thing is brightness. A single star in a far shell looks dimmer than that same star would in a near shell. This is the familiar fact that things grow fainter with distance, and it follows a precise and elegant rule called the inverse square law. The light a star pours out spreads itself over an ever-growing sphere as it travels away. double the distance, and that same light is now spread over 4 times the area, so any small patch of it, such as the patch your eye or your telescope catches, receives only a quarter as much. Triple the distance, and the light is spread over 9 times the area, so you catch only a ninth. The brightness falls off as the square of the distance, so the stars in a shell twice as far away each appear only a quarter as bright. This is exactly the fading that Halley reached for, the hope that the distant stars might simply be too faint to matter. On its own, this fading does seem to promise that the far shells dwindle into insignificance. But there is a second thing that changes as we move outward, and this is the piece Halley missed, the piece that makes the paradox truly bite. As we move to a more distant shell, that shell is bigger. It is a larger sphere, so it has more surface, more room in its thin layer, and therefore it holds more stars. And here is the quiet beauty of it. The surface area of a sphere grows as the square of its radius by exactly the same square law that governs the fading of the light, only running in the opposite direction. A shell twice as far out has 4 times the surface area, and so, if the stars are spread evenly through space, it contains 4 times as many stars. A shell 3 times as far holds 9 times as many. The number of stars in a shell grows as the square of the distance. Now set the two effects side by side and watch what happens. Move to a shell twice as far away. Each star in it is only a quarter as bright, but there are 4 times as many of them. 1 quarter multiplied by 4 is exactly 1. The dimming and the multiplying cancel perfectly, completely. The shell twice as far away, with its fainter but far more numerous stars, sends you precisely the same total amount of light as the nearer shell did. Move to a shell 3 times as far. Each star is a ninth as bright, but there are 9 times as many. A ninth multiplied by 9 is, once again, exactly 1. The same total light arrives. This is the very heart of Olbers' paradox, and it is worth pausing on, because it is so clean it almost feels like a conjuring trick, and yet it is simply, soberly true. Every shell of space, no matter how near or how impossibly far, contributes the same total amount of light to your sky. The fading of distance is exactly and forever balanced by the multiplying of the stars. The far shells are not negligible at all. A shell at the very edge of the observable universe pours just as much light toward you as the shell of stars in our own cosmic neighborhood. Distance does not save you. It cannot. The geometry has built into itself a perfect, eternal compensation. And now the conclusion arrives with the full weight of all those shells behind it. If every shell sends the same amount of light, and the universe is infinite, so that there are infinitely many shells stretching outward without end, then the total light reaching you is that same amount added to itself without limit. It is endless. The sky should be flooded with light, not merely a little brighter than we see, but overwhelmingly, impossibly bright, every point of it blazing. Of course, the real sky cannot literally be infinitely bright, and there is a refinement that brings the prediction down from infinity to something physical and concrete. The refinement is this: stars are not mathematical points. They have real surfaces, real sizes. And a nearer star will block our view of a more distant star that happens to sit directly behind it, the way a tree close to you can hide a whole forest behind it if you stand in the right spot. So you cannot truly stack an infinite number of stars along a single line of sight. Sooner or later, looking in any direction, your gaze lands on the surface of some star and stops there, unable to see past it. But notice what that means, and it is the crucial point. It does not rescue the dark. It only changes the answer from infinitely bright to a sky as bright as the surface of a typical star, because every single line of sight, near or far, still ends on a stellar surface somewhere. To feel why that is so devastating to any hope of a dark sky, we need one more idea, a quiet and slightly surprising one, called surface brightness. Here it is. When you look at the glowing surface of a star, its surface brightness, how brilliant that surface appears patch for patch, does not actually depend on how far away the star is. This sounds wrong at first. Surely a distant star's surface should look dimmer, but consider what distance does. As a star recedes, yes, the total light reaching you from it falls by the inverse square law, growing fainter and fainter. But at the very same time, the star appears smaller, shrinking in your view, so that all of that dimming light is gathered into a smaller and smaller patch of sky. The two effects, the dimming and the shrinking, cancel exactly. The result is that any patch of a star's surface, however near or far the star is, shines with the same surface brightness. The sun's surface and the surface of a star 10,000 light-years away, taken patch for patch, are equally luminous to your eye. The distant one is simply too small for your eye to resolve as a disk. There is an everyday version of this that you have seen without ever thinking of it as physics. Picture a long wall, painted a single even color, stretching away from you down a street. Stand close to it, and a patch of the wall fills your view with that color. Now walk backward, further and further from the wall. Does the color of the wall grow dimmer as you retreat? It does not. The wall looks just as bright a yellow, or a white, or a blue from across the street as it did up close. What changes is only how much of your view it fills, not how bright it appears patch for patch. Same is true of a clear daytime sky, or a wide field of snow, or the glowing face of a star. A surface holds its brightness with distance. It only shrinks. And so a sky tiled in every direction with the surfaces of stars would shine with the full brightness of a stellar surface, no matter that those surfaces lie at every distance from near to unthinkably far. Distance shrinks them. It does not dim them. Now put that together with the stacking. If every line of sight ends on a stellar surface, and every stellar surface, no matter its distance, shines with the same surface brightness as the sun's, then every direction you look should glow as brightly as the surface of the sun. The entire sky, from horizon to horizon, should burn with the brilliance of the sun's own face. Whether you do the simple sum or this careful occlusion-corrected one, the prediction lands in the very same place. The whole sky should blaze, with no dark anywhere between the stars at all, because there would be no dark, only an unbroken sheet of stellar fire. And here is a way of feeling that conclusion that is, if anything, even more vivid than its brightness, and it carries us quietly toward where the whole story is going. If the entire sky shone with the surface of the sun, then it would not merely be blinding, it would be hot. The surface of the sun burns at something like 5,500 degrees. A sky covered, in every direction, with stellar surfaces would bathe the earth in that same fierce heat from all sides at once, with no cool dark anywhere to radiate the heat away into. The whole world, and everything on it, would be driven up toward the temperature of a star's surface. The oceans would boil away. The rocks themselves would glow and run. In an infinite, eternal, static universe, the night sky would not just be bright as the sun. Everything beneath it would slowly come to the same searing temperature as the sun, because there would be nowhere colder for the heat to escape to. So the gentle dark above you tonight is not only a visual fact, it is a thermal one. The night is cool. And a truly infinite, eternal, star-filled universe in the end could not be cool. Hold on to that quietly. The idea that the dark and the cool belong together. Because when we finally find the glow that does fill the whole sky, much later in our journey, the first thing we will measure about it is precisely its temperature, and it will be one of the coldest things there is. That is the prediction, laid bare and made rigorous. And it is wrong. Spectacularly, obviously, every single night wrong. The sky is dark. The sun's face does not fill the heavens at midnight, and the world is not seared to a stellar heat. So we are forced back to the three pillars, and now we know the prediction was no loose or careless guess. The geometry is airtight. The arithmetic balances to the last decimal, and even the careful refinement, accounting for the real sizes of stars and the surface brightness rule, only confirms the blaze. If the three pillars all stand, the bright sky follows with the certainty of 2 and 2 making 4, which means that one of those pillars cannot stand. The dark sky, that gentle, ordinary dark you have looked at on every night of your life, is quietly telling us that the universe is not what those three old assumptions describe. This was understood with real clarity by the close of the 19th century. The British physicist Lord Kelvin, William Thomson, one of the great minds of his age, took up the problem in the years around 1901 and worked it through with proper rigor. Kelvin did the calculation carefully and arrived at a key insight that points straight toward where our story is heading. He reasoned that even in a vast universe of stars, the sky could remain dark if the universe were not old enough, and the stars not long-lived enough, for the light from the most distant shells to have arrived yet, or for enough stars to have shone for long enough to fill the sky. In other words, Kelvin saw that the resolution might lie not in dust, or in some special arrangement of the stars, but in time, in the finite age of things. He did not have the full modern picture, the expanding universe and its beginning, which was still decades away from being discovered. But he correctly grasped that a young enough universe, or one whose stars had simply not been burning long enough, would naturally have a dark sky, no matter how many stars it contained. More than 100 years ago, working only with the physics of his own time, Kelvin had already put his finger on the doorway. The answer was hiding in time all along. So which pillar breaks? We can already feel the shape of the answer beginning to form, even before we can name it fully. People reached for the dust between the stars, for the idea of a finite edge, for the thought that stars might thin out at great distances, each of them hoping to save the comfortable old picture of a universe that was infinite, settled, and eternal. Each attempt was thoughtful. Each one seemed for a while as if it just might work, and each one, when followed carefully all the way to its end, quietly failed, for reasons that are themselves beautiful to understand. Those three failed rescues are where we turn next. They are worth meeting not because they are foolish, but because of exactly how they are wrong. The way each one collapses teaches us something true about how the universe holds itself together. We will walk through them slowly, the way we have walked through everything so far, and we will see why the dark cannot be cheated by dust, or by an edge, or by a thinning of the stars. The only way out, it will turn out, just as Kelvin began to glimpse, is to let one of the great pillars gently fall. So one of the three pillars has to fall. Infinite, static, eternal. At least one of them is false, because the geometry is airtight and the sky is dark. But the people who first felt the weight of this did not want to let any of the pillars go. The picture of a universe that was endless, settled, and eternal was a comfortable one, even a beautiful one, the kind of cosmos that feels stable and permanent and safe. And so for a long while the instinct was not to break a pillar at all, but to find some other escape, some clever feature of the cosmos that could quietly swallow the excess light and leave the old picture standing whole. 3 such escapes were proposed, each one thoughtful, each one tempting, and each one failed in a way that teaches us something real about how the universe is put together. Let us walk through them in turn, gently, because the manner of their failing is half the pleasure. The first and most natural idea is dust. Heinrich Olbers himself reached for it, which is fitting, since his name is on the puzzle. If the space between the stars is not perfectly clear, if it is filled here and there with vast clouds of dark, cold dust and gas, then perhaps that dust simply absorbs the light of the most distant stars before it can ever reach us. The far shells of the universe would still be blazing away, but their light would be soaked up by the dark clouds in between, intercepted along its long journey, and so our sky could stay dark and quiet. It is a genuinely appealing thought, and it is not built on fantasy, because we know that interstellar dust is real. There truly are great obscuring clouds out there, dark lanes that block the light of the stars behind them. You can see them with your own eyes on a clear, dark night, as the dark rifts and channels that thread through the soft, glowing band of the Milky Way, places where the light of distant stars is being blocked by clouds of dust between us and them. So the dust is not imaginary at all. The only question is whether it can do the job of keeping the whole sky dark forever. And the answer, when you follow it carefully to its end, is that it cannot, for a reason as deep and as certain as any in all of physics. The reason is the conservation of energy. Energy is never destroyed. It only changes its form, passing from one kind into another, never vanishing from the books. So when a cloud of dust absorbs starlight, that light does not wink out of existence. The energy it carried does not disappear. It goes into the dust, and what it does there is warm it. The dust grows hotter. And here is the quiet trap that closes slowly around this whole idea. We are imagining, remember, a universe that is eternal, that has existed forever and will exist forever. Give a dust cloud forever to sit and soak up starlight, and it does not simply warm a little and then stop. It keeps warming and warming until it reaches what physicists call thermal equilibrium, the point at which it is radiating away exactly as much energy as it absorbs. It cannot hold the heat in indefinitely. There is nowhere for the energy to hide, and a warm object glows. This is one of the most basic facts about matter. Everything with a temperature radiates light. That is simply what warm matter does, and the warmer it grows, the more it glows, and the bluer and brighter that glow becomes. So given infinite time, the dust heats up until it is glowing just as fiercely as the very starlight it was meant to be blocking. It does not darken the sky at all. It becomes another source of light in the sky, shining with the same brightness as the stars whose light it swallowed. Picture it slowly, because it is a strangely beautiful image. A vast dark cloud hanging in the deep void, century after century, age after age, eon upon eon, quietly drinking in the light of 1 billion distant suns. It cannot send that energy off to nowhere. It can only hold it for a while as warmth, and then, glowing first a dull and sullen red, then orange, then brighter and whiter still, it begins to shine the light back out into space. Over a true eternity, the cloud that was meant to hide the stars ends up burning as bright as they do, indistinguishable from them. The dust does not solve the paradox, It only relocates the glow, moving it from the stars to the dust and changing nothing about the brightness of the sky. And so the first rescue collapses, defeated not by any telescope or observation, but by a law as simple and as unbreakable as the idea that you cannot make energy quietly disappear. The second idea is more direct, and it is the one Kepler himself had imagined centuries before. Perhaps the universe of stars is simply finite. Perhaps there is an edge, not necessarily an edge to space itself, but an edge to the distribution of stars, a distance beyond which the stars run out, and there is only empty void stretching on. If the stars come to an end at some distance, then the infinite stacking of shells that the geometry demands never actually happens. There are only so many shells, only so much light, and beyond the last of them, true darkness. This was Kepler's great dark wall enclosing the stars, and it has an honest appeal. It would resolve the paradox at a single stroke. The pillar of an infinite universe would fall, the endless sum of starlight would be cut off, and the dark sky would follow naturally. The trouble is that we have looked harder and harder for centuries now, and we have never once found the edge. Every time our instruments improved, every time we could see fainter and deeper into space, the very same thing happened. We did not find a boundary, a final shell of stars with emptiness beyond it. We found more. When the great observer William Herschel, working in England in the late 18th century with telescopes he built and polished with his own hands, swept the heavens and counted stars, he kept finding them in every direction his growing mirrors could reach, deeper and deeper, with no sign of any limit. As telescopes grew larger through the 19th and 20th centuries, the faint smudges of light that some had taken for nearby clouds of gas resolved, one by one, into entire separate galaxies, vast island universes of their own, each holding billions of stars, receding into the distance further than anyone had dared to imagine. It was Edwin Hubble in the 1920s who finally proved that those spiral smudges were galaxies far beyond our own Milky Way, and at a stroke the known universe grew almost unimaginably larger. And in our own age, the deep fields we spoke of earlier, Hubble staring for 10 days into a grain of sky and pulling out 3,000 galaxies, the ultra-deep field pulling out 10,000, James Webb reaching further still into the infrared, have only confirmed it without any limit in sight. The deeper we look, the more galaxies appear. There is no thinning toward an edge, no final wall, no sign anywhere of the void where the stars are supposed to stop. Out to the very limit of what we can observe, the universe stays full. The edge has never been found, because as far as the stars and galaxies themselves are concerned, there does not appear to be one. So the second rescue fails as well, defeated by the simple, patient, centuries-long act of looking deeper and always finding more. The third idea is the most sophisticated of the three, and it takes a little more care to set up properly. It goes like this. What if the stars are arranged in a special kind of pattern, a hierarchy, in which the density of matter thins out as you move to larger and larger scales? Imagine stars gathered into clusters, and clusters gathered into larger groupings, and those gathered into larger ones still, but arranged in such a way that the bigger the scale you consider, the more empty space there is between the clumps. The universe could still be infinite in extent, but it would be built like a kind of fractal, a structure that looks broadly similar at every scale, yet grows ever more sparse, ever emptier as you zoom outward. In such a universe, the distant shells, though they would exist, would be mostly empty, holding far fewer stars than the simple even spreading we assumed in the geometry. The light would not add up the way the paradox demands, because the far shells would be nearly vacant, contributing almost nothing. And so, once again, the sky could remain dark while the universe stayed comfortably infinite and eternal. This was a serious proposal, taken seriously by serious people, and on small and moderate scales, it even holds a real grain of truth. The universe genuinely is clumpy when you look at modest distances. Stars gather into galaxies. Galaxies gather into groups and clusters. And those clusters string themselves together into enormous threads and sheets and filaments, a vast tangled structure that astronomers call the cosmic web, with great emptier regions, the cosmic voids, lying between the strands. It is one of the grandest patterns in all of nature, a cobweb of galaxies spun across hundreds of millions of light years, and it really does look, at first glance, like it might just go on growing more and more hierarchical at every larger scale. For a long time, it was a genuinely open question whether that clumping continued forever, ever sparser and more clustered without end, or whether, at some scale, it finally smoothed itself out. And the only way to settle it was to map the universe on the very largest scales we could reach and look. And in our own time, we have done exactly that. Enormous surveys have charted the positions of millions upon millions of galaxies across huge volumes of space. The greatest of them, the Sloan Digital Sky Survey, has been operating from the Apache Point Observatory in the mountains of New Mexico since the year 2000, patiently measuring the distances to millions of galaxies, one after another, and from all those measurements building a three-dimensional map of the cosmos that reaches out across billions of light years. It is one of the most ambitious acts of map-making our species has ever undertaken, a chart not of a coastline or a country, but of the universe itself. And what these great maps reveal is decisive. Yes, the universe is clumpy on the scales of galaxies and clusters and the cosmic web, all those filaments and voids. But when you step back far enough, to scales of a few 100 million light years and beyond, the clumpiness smooths away. The web blurs into an even texture. On the largest scales, the universe is remarkably, almost eerily uniform. Pick any large enough region, anywhere at all, in any direction you choose, and it contains very nearly the same amount of matter as any other region of the same size. The cosmos is, in the language of cosmology, homogeneous and isotropic, the same everywhere and the same in every direction. There is no endless fractal thinning. The clumping has a definite limit, and beyond that limit, the universe settles into a smooth, even, brimming fullness. So the far shells are not empty after all. They hold their fair share of galaxies, just as the original geometry assumed they would, and the third rescue falls quietly with the other two. So there it is, 3 thoughtful attempts to save the old, comfortable picture, and 3 quiet failures, each one collapsing for a reason of its own. Dust cannot hide the light, because given time it warms until it glows with the very light it absorbed. A finite edge cannot save us, because we have looked and looked for centuries and never found one. A thinning fractal cannot save us, because the great surveys show the universe is smooth and full on its larger scales. And notice the single thread that runs through all 3 of them. Every one was an attempt to keep the universe infinite, static, and eternal, to leave all 3 pillars standing untouched, and find some other way to dim the sky. And every one of them failed. The light will not be hidden. The universe will not be bounded. The stars will not be thinned. We have run, gently and completely, out of ways to cheat, which means the answer was never going to come from some clever feature of the stars, or the dust, or the arrangement of matter in space. The answer has to come from the pillars themselves, One of those three deep assumptions, infinite, static, eternal, simply is not true of the universe we actually live in. And once we accept that, once we stop trying so hard to save all three at once, and instead ask calmly, which of them the universe is quietly telling us to release, the dark sky stops being a paradox at all. It becomes a clue, and a clear one, pointing straight at the real nature of the cosmos. It turns out, just as Lord Kelvin began to glimpse a century ago, that the universe is not eternal, and it is not static. And the moment we truly understand what it is instead, the darkness overhead will finally, gently, beautifully make sense. That is where we are going now, into the heart of the answer itself, where everything we have so patiently built begins, at last, to resolve. So we let a pillar fall. After 4 centuries of looking, after every clever rescue has quietly failed, the universe leaves us no choice. And it turns out we have to give up 2 of the 3 great assumptions, not just one. The universe is not eternal, and the universe is not static. Only the first pillar, that the cosmos is vast and full of stars in every direction, survives intact, confirmed again and again by the deep fields. The other 2 were where our intuition quietly went wrong. And the moment we accept that, the dark sky stops being a paradox and becomes, instead, one of the simplest and most direct pieces of evidence we have for the kind of universe we actually inhabit. Let us take the 2 fallen pillars one at a time, slowly, because each one entirely on its own would be enough to darken the sky, and together they settle the matter completely. Begin with the pillar of eternity, the assumption that the universe has existed forever, with no beginning behind it. We now know that it has not. The universe had a beginning, roughly 13.8 billion years ago. Everything we can see emerged from an unimaginably hot, dense state in the event we have come to call the Big Bang. Space itself, time itself, all the matter there is, all of it traces back to that single beginning. The cosmos is not infinitely old. It has an age, a finite span of years behind it, a birthday of sorts, and that one fact all by itself is enough to make the night sky dark through a consequence that is one of the most quietly profound ideas in all of science. The consequence is this: light travels fast, but it does not travel instantly. It moves at a fixed and finite speed, about 300,000 kilometers every second, which is breathtakingly quick by any human measure, and yet utterly finite, with a definite limit. And because light takes real time to cross space, when we look out at a distant object, we are never seeing it as it is right now. We are seeing the light that left it long ago, light that has been traveling toward us across all the years in between. To look out into space is to look back in time. There is simply no way around it. Every single glance into the depths of the sky is a glance into the past. You feel a small version of this even close to home. The light from our own sun takes about 8 minutes to reach us, so we never actually see the sun as it is in this moment, only as it was 8 minutes ago. If the sun was somehow to vanish, we would carry on seeing it shining peacefully for 8 more minutes before the darkness arrived. The nearest star beyond the sun lies more than 4 light years away, which means its light has been traveling for over 4 years before it touches your eye. So you see that star tonight not as it is, but as it was 4 years ago. Look at a galaxy that lies 1 million light years off, and you are seeing light that began its journey 1 million years before there were cities, before there was writing, before much of human history had even begun to unfold. The further out you look, the deeper into the past you are seeing. In the cosmos, distance is time. The two are bound together by the steady, finite pace of light. And now the two ideas meet, the finite age of the universe and the finite speed of light, and between them they quietly close the sky. Because if the universe is only 13.8 billion years old, then light has only had 13.8 billion years in which to travel. No light can possibly have reached us from any source more distant than the distance light could cross in that span of time. Look far enough out, and you are looking back toward a time near the very beginning, back before the first stars had formed, back when there were no stars at all to shine. There is, in effect, a horizon, not a wall, not a physical edge to space itself, but a limit on how far we can possibly see, set by how long the universe has existed and how fast light is able to travel. Beyond that horizon, there is starlight that has not arrived yet. It may well be out there streaming toward us even now, but it is still in transit, still crossing the immense gulf, not due to reach us for ages and ages to come. This is the resolution of the whole geometric argument we built so carefully. Remember the nested shells, each one contributing the same amount of light, an infinite stack of them flooding the sky to the brilliance of the sun. The reason the sky is not flooded is that the stack is not infinite. It is cut off sharply by the horizon. The far shells, the ones lying beyond the reach of 13.8 billion years of travel, simply have not had time to send their light to us yet. The sum of starlight, which the old eternal picture made endless, is in a young universe a finite sum, gathered only from those shells near enough for their light to have completed the journey. The infinite blaze never assembles, because most of the universe's light is still on its way, or comes from a time so early that the stars had not yet been born. The dark between the stars is, in part, simply the dark of distances whose light has not arrived. The far sky is dark because it is, in a sense, still loading, still arriving, photons travelling toward us across a cosmos too young for them to have finished the trip. This is precisely what Lord Kelvin had begun to glimpse a century ago, when he saw that a young enough universe would have a dark sky, no matter how full of stars it was. He had the doorway. He did not yet have the room beyond it. That alone would darken the sky. But there is a second fallen pillar, and it deepens the darkness further still, in a way that is even stranger and more beautiful. The universe is not static. It is expanding. Every part of it is gently drawing away from every other part, the whole vast structure swelling with the passage of time. This was one of the great discoveries of the 20th century, and the story of how we came to know it is worth telling, because it did not arrive as a guess. It was measured painstakingly, and the measuring rested on a quiet and lovely piece of work done by a woman whose name deserves to be spoken. Her name was Henrietta Swan Leavitt, and she worked in the early years of the 20th century at the Harvard College Observatory as one of a group of women employed to examine and catalogue photographic plates of the stars. While studying a particular kind of star called a Cepheid variable, a star that brightens and dims in a steady, repeating rhythm, Leavitt noticed something remarkable. The brighter a Cepheid truly was, the longer and slower its rhythm of pulsing. The period of its blinking was tied directly to its true luminosity. And this was a gift of enormous value, because it meant that simply by timing how long a Cepheid took to complete its cycle of brightening and dimming, you could know how much light it was truly giving off. And once you know how bright a star truly is, and you compare that to how bright it merely appears in the sky, you can work out exactly how far away it must be. The fainter it looks than it ought to, the more distant it is. Leavitt had found a cosmic measuring stick, a way to gauge the distances to faraway objects, and astronomers call such an object a standard candle. Her discovery, published in the years around 1912, became one of the foundations on which the measurement of the universe was built. It was this measuring stick, among others, that the astronomer Edwin Hubble took up at the Mount Wilson Observatory in California in the 1920s. Using the Cepheids to gauge distances and studying the light of the galaxies, Hubble found something that reshaped our entire picture of the cosmos. Almost everywhere he looked, the galaxies were moving away from us. And more than that, the more distant a galaxy was, the faster it was receding. A galaxy twice as far away was fleeing roughly twice as fast. This steady relationship between distance and speed of recession is now known as Hubble's law, though we know today that the Belgian priest and physicist Georges Lemaitre had arrived at much the same conclusion from theory at nearly the same time. And the meaning of it was profound. This was not because we sit at some special center of things that everything flees from. It was because space itself is stretching, everywhere, all at once. The galaxies are not so much flying through space as being carried apart by the expansion of the space between them. The classic image is of raisins set in a loaf of bread that swell apart as the dough rises in the oven. No raisin is at the center. Yet every raisin sees all the others drawing away from it, and the more distant ones receding fastest, simply because there is more swelling dough between them. The whole cosmos is gently, ceaselessly growing larger. The distances between the galaxies are widening with every passing moment. And an expanding space does something profound to the light traveling through it, something that strikes directly at the heart of our paradox. Picture a wave of light setting out from a distant galaxy, a wave with its little crests and troughs, its particular wavelength that our eyes read as a particular color. As that light crosses the vast gulf toward us, over millions or billions of years, the space it is traveling through is itself stretching, swelling beneath it. And as the space stretches, the light wave riding upon it stretches too. The crests are slowly drawn further apart. The wavelength grows longer. And longer wavelength means the light shifts toward the red end of the spectrum and beyond it. This is the cosmological redshift, and it is worth understanding clearly. It is not the light losing energy by bumping into anything, or struggling against any resistance, or growing tired. It is simply the fabric the light rides upon, expanding, carrying the wave's crests gently apart as it travels. For nearby galaxies, the effect is slight, a faint reddening. But for the most distant sources, whose light has crossed billions of light years through billions of years of relentless expansion, the stretching is enormous. Light that left a young galaxy as ordinary visible light, the kind of light your eye was built to catch, arrives at us stretched so far that it is no longer visible at all. It has been pulled clean out of the narrow band our eyes can perceive, drawn down into the infrared, and for the oldest and most distant light, further still, into the microwave. This is exactly the light that the James Webb Space Telescope was built to gather. The reason it works in the infrared, to catch the visible light of the early universe that has been reddened by its long journey into wavelengths Hubble could not see. The most distant glow in the universe is not absent from the sky. It is shifted clean out of the range our eyes can register. It is shining faithfully, but in colors we simply cannot see. Picture it gently, one last time. A wave of light leaves an infant galaxy near the dawn of time, setting out as a warm, visible glow. For billions of years it travels toward us, and all the while the space beneath it is swelling, drawing its crests slowly apart, its color sliding steadily down the spectrum as it comes, from blue toward red, from red toward infrared, from the seen toward the unseen. By the time it finally reaches us, that once visible light has been stretched into a long, cool, invisible wave. It arrives faithfully. It touches us. But our eyes, tuned only to the narrow band of the visible, register nothing at all. The light is here. We simply cannot see it. And now look at what the two fallen pillars have done, working together. The finite age cuts off the far shells, so that most of the universe's starlight has not reached us at all, and never will in our lifetimes. And the expansion stretches whatever light does reach us from the most distant sources, sliding it out of visibility entirely. Between them, the infinite blaze that the old geometry so confidently predicted is reduced to the gentle scattering of stars we actually see, set against a dark that is not truly empty, but full of light we are simply not equipped to perceive. The pillars of eternity and stillness have fallen, and with them the bright sky. The dark is explained. It is worth saying that the modern picture this rests upon, which cosmologists call the Standard Model, or lambda CDM, is held together by an enormous body of careful measurement, from the expansion Hubble and Lemaitre found, to the deep precision of the great space missions that came later. It is not a loose story. It is among the most thoroughly tested frameworks in all of science. There are still genuine puzzles within it, honest open questions. One of them is gently teasing at cosmologists even now. When we measure how fast the universe is expanding by studying nearby galaxies, using Cepheids and exploding stars as our standard candles, we get one value for the rate. When we measure the same expansion rate from the light of the very early universe, we get a slightly different value. The two disagree by a small but stubborn amount, and no one is yet quite sure why. It is called the Hubble tension, and it is not a flaw in the picture so much as a loose thread, the kind of small discrepancy that has, more than once in the history of science, turned out to be the edge of something new and important. There is no need to resolve it tonight. It is simply a reminder that the universe still holds questions, even at the heart of what we understand best, and that the work of looking up is not finished. But we have not quite reached the very bottom of our own question, because if all that distant light is merely shifted out of our vision, rather than truly gone, then a quiet question follows, almost on its own. What if we could see it? What if our eyes were tuned not to the narrow band of the visible, but to those long, stretched, invisible waves? What would the sky look like then? Would it still be dark? Or would something be waiting there, filling the whole sky after all, exactly as Olbers' geometry promised it must, just glowing in colors we were never built to see? That question has an answer, and it is where we are going next, slowly. So here is what the dark has been keeping all along. The night sky is not dark. It only looks dark to us. If our eyes were built a little differently, if they could see the long, stretched, invisible waves instead of the narrow band of the visible, we would look up and find the entire sky glowing. Not in scattered points, everywhere. A smooth, seamless, uniform light filling every direction at once, exactly as Olbers' geometry promised it would, with no dark between the stars at all. The blazing sky the paradox predicted is real. It is up there right now, in every direction you could possibly turn. We simply cannot see the color that it shines in. That glow has a name. It is called the cosmic microwave background, and it is the oldest light in all the universe. To understand where it comes from, we have to travel back, gently, to the very early cosmos, to a time long before there were any stars or galaxies at all, when the whole universe was a single, glowing fog. In the beginning, in the first stretch of time after the Big Bang, The universe was unimaginably hot and dense, far too hot for atoms to exist. Matter was a seething plasma, a soup of bare particles, protons and electrons, and light all churning together, so crowded and so fiercely energetic that no atom could ever hold itself together. The moment an electron tried to settle around a proton to make an atom, the surrounding heat would tear it away again, and in that state, the universe was opaque. Not dark, but opaque, the way the inside of a thick fog is opaque, or the way the glowing interior of the sun is opaque, even though it blazes with light. The light could not travel freely. Every time a ray of light tried to set out across that early cosmos, it ran almost at once into a free electron and was scattered, knocked aside, sent off in some new direction, only to strike another electron and scatter again and again and again. The light was trapped, bouncing endlessly among the crowded particles, unable to go anywhere at all. The whole universe was a glowing, foggy, luminous cloud, brilliant everywhere yet unable to let a single ray of its light loose. And then the universe did what it has been doing ever since. It expanded, and as it expanded, it cooled. Slowly, over many thousands of years, the seething plasma grew less fierce, the temperature falling steadily as the cosmos swelled outward. And about 380,000 years after the beginning, the universe cooled past a critical point, down to around 3,000 degrees, cool enough at last for something new and wonderful to happen. The bare protons and electrons, which had been flying free all that time and scattering the light, could finally come together and join. They combined into the first stable atoms of hydrogen, and the heat was no longer strong enough to tear them apart again. And in that moment, all across space, the fog lifted. This moment has a name. Astronomers call it recombination, or sometimes simply the moment of decoupling, the moment when light and matter parted ways and went their separate paths. Because once the free electrons had all been swept up into atoms, there was nothing left to scatter the light. The obstacles were simply gone. And the light that had been trapped for 380,000 years, bouncing endlessly in the fog, was suddenly set free to travel in straight, clear lines. The universe became transparent, all at once, everywhere, in every direction. The fog became clear glass. And the light of that primeval glow, released in that single instant across all of space, set out to travel freely through the now clear cosmos. It has been traveling ever since. It is still traveling now. It is, in a real sense, the most ancient thing it is possible to see. That released light is the cosmic microwave background. It is the light of the universe's own glowing infancy, the afterglow of the hot beginning, set loose at the very moment the fog cleared, and journeying outward through space ever since, for 13.8 billion years. And here is the thing to hold gently, the thing that connects it back to our whole long puzzle. That light fills the entire universe. It was released everywhere at once, in every direction, from the whole glowing fog that was the early cosmos, which means it comes to us now from every direction too. There is no patch of sky it does not fill. It is the uniform, seamless glow that Olbers geometry demanded, the bright sky in every direction, and it has been quietly bathing the heavens this whole time, on every night anyone has ever looked up. But it does not reach us as the fierce glow it once was. Remember the expansion and what it does to light traveling across the ages. When that light was first set free, the universe was about 3,000 degrees, and the glow it sent out was a warm, reddish-orange light, something like the surface of a cool star. But for 13.8 billion years, That light has been crossing an expanding universe, and all that while the space it travels through has been stretching, drawing its waves longer and longer and longer. The light has been redshifted by an enormous factor, its wavelength stretched roughly 1,000-fold, and as its waves stretched, the light cooled, sliding down from the warm orange glow of 3,000 degrees all the way down to a faint, cold whisper. Today, that ancient light arrives at a temperature of just 2.7 degrees above absolute zero, which is the coldest temperature there is, the point at which all warmth runs out. The glow has been stretched out of the visible, out of the infrared, and all the way down into microwaves. That is precisely why we cannot see it with our eyes. The blazing sky is still there. It has only cooled and stretched, over 13 billion years of expansion, into a color far below the reach of human sight. So the sky truly is glowing uniformly in every direction, exactly as the paradox said it must. The geometry was right all along. The early thinkers who expected a blazing sky were not wrong about the glow. They were only wrong about its color, because they could not possibly have known that the universe had a hot beginning, or that the expanding cosmos would cool that beginning's light all the way down into invisible microwaves. The dark we see with our eyes is the bright sky they predicted, simply shifted gently out of view. The night is full of light. We have been looking straight at it the whole time, on every dark night of our lives, without knowing. And this is not merely a piece of theory worked out on paper. We have actually heard this ancient light. We found it, and the way we found it is one of the quiet, almost comic accidents of all of science. In the year 1965, 2 engineers at Bell Telephone Laboratories in Holmdel, New Jersey, Arno Penzias and Robert Wilson, were working with a large, sensitive horn-shaped antenna, an instrument originally built for early satellite communication. They were trying to make careful radio measurements of the sky, and to do that properly, they needed to track down and eliminate every last source of stray noise in their equipment. But there was a faint hiss they simply could not get rid of. A low, steady, persistent static that was there no matter where they pointed the great antenna, by day or by night, in every direction equally, never changing, never fading. It seemed to be coming from everywhere at once. They went to genuinely extraordinary lengths to hunt down its source. They checked every circuit and connection. They considered radiation leaking from the nearby city, and from the Earth's atmosphere, and from the stars. They even discovered that a pair of pigeons had nested inside the great horn of the antenna and coated parts of its interior with droppings, which they delicately and famously described in their notes as a white dielectric material. So they cleaned it all out, and they shooed the pigeons away, and still the hiss remained, faint and steady and everywhere. It would not go away. It came uniformly from the whole sky, from every direction they aimed at, and they could not for the life of them explain it. What they did not know at first was that not far away, at Princeton University, a group of physicists led by Robert Dicke had been working out the theory that the hot early universe should have left behind exactly such a glow, a faint relic radiation coming uniformly from all directions, the cooled afterglow of the beginning, and they were preparing to go looking for it. When the two groups finally learned of each other and connected, the meaning of that stubborn hiss became suddenly, beautifully clear. Penzias and Wilson had not found a flaw in their equipment after all. They had found the cosmic microwave background. That persistent static in their antenna was the cooled, stretched light of the universe's own birth, arriving from every direction at once across 13.8 billion years. The very glow that our whole paradox had been pointing toward all along. The discovery earned Penzias and Wilson the Nobel Prize in Physics, and it stands today as one of the great confirmations of how our universe began. Sit with that for a moment, slowly. Two men in New Jersey, wrestling with a faint hiss in an antenna, cleaning out pigeons, checking and rechecking every wire, and the noise they could not silence turned out to be the oldest light in all of existence, still arriving, still filling the sky, still falling softly upon the earth and upon everything else, as it has without pause for 13 billion years. They had built themselves an ear, and without ever meaning to, they had heard the beginning of the world. And in the decades that followed, we did not merely hear that ancient glow. We learned to map it in finer and finer detail with a series of spacecraft built for exactly that purpose, and each one deepened the wonder. The first was a NASA mission called COBE, the Cosmic Background Explorer, launched in 1989. COBE measured the colors, the spectrum, of that ancient light with such precision that it confirmed something remarkable. The glow matches almost perfectly the kind of light given off by a warm object at a single temperature, what physicists call a blackbody, a smooth and characteristic signature. It was exactly the light a cooling fireball should leave behind, just as the theory had predicted, and the match was so exquisite that it removed nearly all remaining doubt about the hot beginning. And COBE found something more. It detected, for the very first time, that the glow is not perfectly, boringly uniform. There are faint ripples in it, incredibly subtle variations in temperature from one part of the sky to another, differences of only about 1 part in 100,000. Tiny, almost nothing. But those tiny ripples were the seeds of everything. They were the slightly denser patches in the early universe, the gentle clumps that gravity would slowly draw together over billions of years into the galaxies, the clusters, the whole great cosmic web we spoke of earlier. The two scientists who led that work, John Mather and George Smoot, later received the Nobel Prize for it. We were, in a sense, looking at a baby picture of the universe, and reading in its faint mottling the first faint outlines of everything that would one day come to be. Two later missions sharpened that baby picture further still. NASA's WMAP spacecraft, launched in 2001, mapped those faint ripples across the whole sky in far greater detail, and from their precise pattern, astronomers were able to read off the age of the universe, its overall shape, and what it is made of, with a precision no one had imagined possible. And then, the European Space Agency's Planck mission, launched in 2009, mapped the ancient glow more finely yet, refining our picture of the cosmos to a remarkable sharpness, confirming again and again the same essential story. A hot beginning, a cooling and expanding universe, an ancient light stretched into microwaves and raining down on us from every direction. 3 spacecraft, each one listening more carefully than the last to the same faint whisper that Penzias and Wilson had stumbled upon by accident, and each one finding the same beautiful truth written there. And so the dark sky, the gentle, ordinary dark you have looked at on every night of your life, is not empty at all. It is full. It is filled, edge to edge, and in every direction, with the faint, cool, ancient glow of the universe's very first light, the afterglow of the hot beginning, stretched by 13 billion years of expansion into a whisper that lies just below the reach of your eyes. The darkness overhead is not absence, it is presence. It is the oldest light there is, the record of where absolutely everything came from, raining down upon you softly and silently, as it has on every night of your life, and on every night long before there was anyone here at all to look up and wonder at it. We are bathed in it, right now, in this very room, in the soft dark behind your closed eyes. The ancient light is here, passing through gently, the warm and cooled echo of the moment everything began. The night is not cold, and it is not empty. It is a quiet, gentle sea of the universe's first light, and we are resting, all of us, inside it. And that is the answer to the question we began with all those hours ago. Let us carry it home. So let us come home now, back from the edge of the expanding universe, back across the 13 billion years and the cooling light and the long, patient shells of stars, all the way back to here, to the quiet room, to the soft dark around you and the gentle weight of your own body resting, and the slow rhythm of your breathing, which has been carrying on faithfully this whole time, while we wandered all the way out to the beginning of everything and back again. There is nothing left to solve tonight. The question we started with all those hours ago has been answered, gently and completely. The sky is dark because the universe is young, with a beginning behind it, so that the light of the farthest stars has not yet had the time to arrive. And the sky is dark because the universe is growing, stretching the most ancient light far below the reach of our eyes. That is all. That is the whole of it. You can set the entire puzzle down now, the geometry and the shells, the three pillars, the dust and the edge, and the fractal that all quietly failed, the redshift and the deep fields and the faint ancient glow. Lay all of it down and let it rest, the way you are letting everything else rest now. But carry this one soft thing with you as you drift. The dark above you, the very same dark you can picture behind your closed eyes, is not cold, and it is not empty. It is full of ancient light. It is a quiet sea of the oldest glow there is, the gentle afterglow of the moment when everything began, falling softly and silently through this room, and through you, as it has on every single night of your life, and on every night long before there was anyone here at all to feel it. You are not lying beneath a cold and empty void. You are resting inside a warm and ancient light, a faint and steady glow that has traveled the whole long age of the universe simply to be here, with you, now, in this room, on this night. There is something kind in that, something deeply settled. The cosmos is not a cold and lonely emptiness with a few scattered fires flickering in it. It is full, edge to edge and in every direction, with the light of its own beginning, and we are held gently within it, wherever we happen to be. Nothing about that asks anything of you at all. It does not need you to understand it, or remember it, or do anything with it. It is simply true, and it is simply here, a soft and constant and patient company in the dark, the way it has always been. So let your breathing slow just a little more. Let the last few threads of the day loosen and drift away, one by one, like leaves let go on slow water. There is nowhere you need to go, and nothing you need to reach for, and no part of any of this you need to hold on to. The vast, ordered, ancient cosmos is turning quietly all around you, as it always has, and it has held itself together for 13 billion years, and it will go on holding while you sleep. You are a small, warm, living part of something immense and gentle and old beyond imagining, and you are exactly where you belong in it. Let the questions rest. Let the stars keep their slow turning without you for a while. There is nothing to watch over, nothing to finish, nothing the morning cannot hold for you until it comes. Rest now. Let the ancient light carry you down softly into sleep and sweet dreams.